Hello friends, today we'll start with the heat transfer. We're just gonna go for a brief overview what is heat transfer, different modes of heat transfer, and then we're gonna start with the steady state of a conduction. First conduction, then in the further lectures we'll go move towards convection. Okay, now first what is heat transfer? We all know heat transfer is basically a heat transfer from a high temperature body towards a low temperature body. It's a basically a very important phenomena from the thermodynamics point of view. Second law of thermodynamics basically deals with the heat transfer. That is, the energy is transferred from a higher temperature body towards a lower temperature body. Now, heat transfer occurs in three different modes. Now, the first mode is the conduction mode, the second mode is the convection mode, and the third mode is the radiation mode. We all know what are conduction, what is convection, and radiation. The conduction is the interaction of the particles within the substance. The substance can be either in the form of a solid, it can be either in the form of a liquid or in the form of a gas. Now, high particles which are at high temperature have high energy. Now, these high energy particles they interact with the low energy particles, thereby transferring the heat from higher particles towards the lower particles, and thus the heat is being transferred from one particular end towards the other end. Now, the Fourier law of heat conduction is basically the rate equation for your heat conduction, and we all know that is what is the Fourier law of heat conduction. That is Q is Ka dt by dx. If the flux is in the given direction, x. If the heat is occurring in the x direction. Then what is convection? Convection, again, it's a two types of. It consists of two mechanisms. One is initially it's the conduction occurring, plus the second mechanism along with the conduction is the motion of the particles, motion of the fluid. So we can say that convection occurs wherever there is a fluid motion occurring. And then finally, what is radiation? Radiation is like heat transfer due to electromagnetic waves propagation, either in a vacuum or either in a medium. Like whatever the rays we are getting from the sun, that is the radiation process. In convection, just like conduction, in convection there is another phenomena. The rate of heat transfer can be determined using Newton law of cooling, which is Q is equal to HA into delta T. We're gonna cover up what is Newton law of cooling later on. Similarly, in radiation, the heat transfer phenomena is represented by a Stefan's Boltzmann constant, which is Q is directly proportional to fourth power of the temperature. That is Q is equal to sigma A T4, where sigma is the Stefan's Boltzmann constant, T is the absolute temperature, and A is the cross-sectional area of the body. Now, in our syllabus, we'll be basically covering up the conduction part, few examples of the conduction, and majorly we'll be focusing on the convection part. Now, in convection, the convection occurs mainly because of the two processes. One is the forced convection, and the other one is the free convection or the natural convection. Now, majorly part in our syllabus is basically we'll be dealing with the forced convection type of convection of a heat transfer. Radiation, we're not going to study radiation to that extent. Clear? So let's start with the first case of heat transfer, that is conduction, steady state heat conduction. Now, we all know what is steady state. Steady state means anything with respect to time is zero. There is no variation of any quantity with respect to time. So let's start with the first basic general equation of energy, that is rate of thermal energy in minus rate of thermal energy out plus there is some generation or maybe some production of energy within the system is equal to 0. 0 because of the steady state. So that's the basic general equation which we'll be using in the steady state conduction. So the first example which we'll consider over here is your plane wall. Plane wall with constant surface temperature. Now consider a plane wall of thickness L. These are the x's. It's 0, it's L over here. The thickness is L. And there are two different temperatures. Over here we have the hot fluid moving. Let's say the temperature of the hot fluid is TB1, and over here there is a cold fluid with the temperature TB2. Let's say the surface area of the wall is A X, which is constant on both the sides. Now the wall temperature at X equal to 0 is TW1 and the wall temperature at X equal to L is TW2. Now what will happen when both the walls comes in contact with two different temperatures? Obviously over here the temperature is quite high, so let's say the temperature flows in this direction, then this profile will be determining the profile, this thing, and then there is this temperature. So this is just a general temperature profile between the two different fluids and a solid body in between them. Clear? Now the heat transfer coefficient on at x equal to 0, let's say over here it is H1, and the heat transfer coefficient at x equal to L is, let's say, H2. Clear? Now for this system, let's consider a small shell of thickness delta x, and we're going to apply the energy balance, that is input minus output plus generation equal to 0 under steady state conditions. Now rate at which heat enters at x equal to 0 in a over here will be, let's say, qx. Rate at which heat leaves at x equal to delta x will be qx plus delta x. And let's say there is no accumulation or rate of generation. Rate of generation is 0. There is no heat produced or generated within the walls. So if we substitute all these terms in the basic equation, so what we have is, that is in minus out plus generation is equal to 0. There is under steady state conditions. So input is qx, output is qx plus delta x equal to 0. So if we divide by delta x, put the limits, delta x approaches 0. So what we have is, we have dqx by dx is equal to 0, obviously the negative sign that goes over here. So what do we have over here? Now q, according to Fourier law of heat conduction, qx is minus ka dt by dx. So if you substitute this term over here, so what we have is, it's ka d square dt x square equal to 0, assuming that these two terms are constant. Initially, let's assume they are two constant. Basically, the thermal conductivity does depends upon temperature, but over here in our case, let's assume it to be a constant, and obviously the area is also constant. So what we have is d square t by dx square is equal to 0, a linear temperature profile. So temperature x is C1x plus C2 upon integration. Now, using boundary conditions at x equal to 0, so we have t equal to tw1 and x equal to L, t is equal to tw2. So for these values, and get the value of C1 and C2. C1 comes out to tw1 and C2 comes out to be tw2. Okay, somewhere I'm wrong. Okay, C2 is tw and C1 comes out to be tw minus tw1 by 2. Corrections. Now if you substitute these values in the main equation, so we have tx, the variation of temperature within the wall, is the difference in the temperature okay, sorry, I'm making corrections over here. It's not 2, it's the length L, x plus tw1. So the nature of the temperature within the wall is of a linear, that is, it varies linearly within the solid surface. This is the linear profile. The temperature variation is linear. Now if we want to calculate heat flux, now heat flux is q is equal to minus ka dt by dx, so which is nothing but ka over L into the basically the temperature differences. That's the heat flux. So rate of heat transfer is nothing but q by a, which is k into the delta t by L, or even I can write it as k delta t by delta x. Clear? Now for a steady state in a plane, for a steady state conduction in a plane where there is no heat generation, there is no heat loss from the surroundings, under steady state condition, the rate of heat transfer is constant. Again repeat, where there is no heat generation, there is no heat loss from the surroundings, from the sides, under steady state condition in a plane wall, the rate of heat transfer is constant. That is, whatever is in, that is equal to out, that is, heat transfer rate is constant. Now suppose if the area, the cross sectional area, it varies, and the thermal conductivity also varies. Area varies with the position and thermal conductivity varies with the temperature. Then the heat transfer, or the Fourier law of heat conduction, can be represented as qx dx by ax equal to k, which is the function of temperature, dt, let's say T1 corresponding to position x1, and temperature T2 corresponding to position x2. So then the Fourier law of heat conduction can be expressed as this thing, where both the area varies with the position and the thermal conductivity varies with the temperature. Now suppose if area is constant and thermal conductivity is independent of the temperature, we know that it's Qx is minus Ka by delta x into delta t. Clear? Now on rearranging the negative sign, let's say the negative sign is adjusted within this delta t. So let me remove this thing. So can it be written as Q equal to delta t upon delta x by Ka? So this is basically your thermal potential difference by thermal resistance. So delta x is the driving force, that is the thermal potential difference, and delta x by Ka is the thermal resistance, the resistance to the heat transfer. So from here we can have the definition of thermal resistance. Thermal resistance is nothing but the ratio of thermal driving potential, that is delta T by Q. Thermal driving potential to thermal heat transfer, that is your thermal resistance. It's exactly the same as what is electric resistance, that is the ratio of potential difference to the current. Now over here we are clearly seeing that the resistance to the heat flow, that is thermal resistance, is directly proportional to the thickness of the material and inversely proportional to the thermal conductivity of the material as well as the cross sectional area of the surface. So thermal resistance we can define in terms of heat flux or the temperature difference, and it depends upon the material thickness, the cross sectional area, and the MOC of the material, MOC of the system. Now let's consider a composite plane wall. Now suppose this was a case of a simple plane wall. Now suppose if we add another plane walls of different material having different temperatures, then so the second case is the composite plane wall. Composite plane wall, let's consider a wall consisting of four different materials. Let's say this is material A, material B, we have material C, and we have material D. There's a hot fluid flowing in this direction, and we have a either direction we can take it, no problem. That's the cold fluid. The hot fluid is at temperature TB2, the cold fluid is having a temperature TB1. So let's represent the temperatures at x equal to 0. Let's say this is TA, not TA, T1, sorry, T1. Over here it's T2, over here it's T3, T4, and T5. That means the temperatures at the intersurface. Now according to the heat conduction steady state, under steady state conditions, the heat through the first system, that is through A it's nothing but Q is T1 minus T2 over delta X, that is A, over Ka capital A. Now capital A is the surface area, Ka is the thermal conductivity of wall A, and delta X is this distance, delta XA. So from here we can write T1 minus T2 as delta XA by Ka into Q. Similarly, for T2, T3, it will be delta XB KB area A into Q. Similarly, T3, T4, delta XC over KC A Q, and T4 and T5, delta XD over KD A Q. Now these are the terms which we got under steady state condition, and there is no generation and there is no heat loss. So that means rate of heat entering over here will be same over here, same over here, same over here, and same over here. All these directions. If you're going to add all these equations, so we have T1 minus T5 and Q and A to take out common. So we have delta XA over KA plus delta XB over KB plus delta XC over KC plus delta XD over KD. So Q for this entire system will be T1 minus T5 over delta XA over KAA plus delta XB over KBA plus so on. So that's the overall heat conduction through this composite wall. So you can write overall, not overall, the heat conduction rate through composite wall. Composite wall or composite system will be overall temperature difference over the summation of thermal resistances. Clear? So this was the simple example of the composite systems. Moving further, if we go towards now the radial system. Now for the radial systems, let's consider a single layer cylindrical wall consisting of a uniform material with a constant thermal conductivity. So it's a homogeneous material with constant K. The inner radius is R1, the outer radius is R2. The inner wall is maintained at temperature T1. The outer wall is maintained at temperature T2. So we need to determine the rate of heat conduction in a cylindrical system. Now for this system, let's consider a shell of thickness delta R. Now the heat flow is in the radial direction. Now again, just like momentum balance, again we're gonna we'll study the heat transfer in the radial direction, the heat transfer on the circumferential direction in the z direction. Clear? Over here we're just considering a simple radial direction, that is the heat is flowing from the inner wall towards the outer wall. Now at any given distance, if the heat input into this wall, it will be QR, and heat output, that is moving outwards from this shell of distance delta r, it will be QR plus delta r. Clear? Now the difference there, let's assume there is no generation, so heat generation is 0, and under steady state conditions, so we're going to have heat input minus heat output equal to 0. So what is in minus out, and if you divide by delta r, so what we left as QR minus QR plus delta r equal to 0. Divided by delta r, limits delta r approaches to 0. So delta r approaches 0. So what we have is minus dq by dr at QR equal to 0. That is now, so QR is constant. QR is constant, right? Now QR, according to Fourier law of heat conduction, is minus Ka dt by dr. Now what is cross-sectional area in a cylindrical system? It will be 2 pi r L. So under steady state conditions, QR is constant, so can we represent it as dt is equal to QR by Ka into dr, and we integrate from r1 to r2, from t1 to t2. So t2 minus t1 is minus, so there's a minus over here, q r over, now area depends upon radius, so this area over here will be over here. Now q by k dr over 2 pi rl, integrating from r1 to r2, will result in t2 minus t1 equal to minus qr over 2 pi l k, they are constant, taken out r r1 to r2, which is minus qr by 2 pi k l ln r2 by r1. So qr, heat conduction through a radial system, is 2 pi kl over ln r2 by r1 into delta t. That is for a single cylindrical layer. This is for a single cylindrical layer. Now suppose if there are two layers, on this same system, let's say this is r1, that's r2, and we have another layer, that is this thing, r3. Now temperature over here is T1, over here it's T2, over here it is T3. Then under steady state conditions, the rate of heat input will be equal to the rate of heat output through all these three different systems. So QR is constant, which can be written as Ka 2 pi L, that is delta T over ln R2 by R1, that is Ka 2 pi L T1 minus T2 over ln R2 by R1. Also, this is also equal to Kb 2 pi L T2 T3 over ln R3 by R2, where Ka and Kb, Ka is the thermal conductivity of the surface and Kb is the thermal conductivity of this surface, that is Kb. Clear? So under steady state conditions, the rate of heat transfer through to both these different materials will be same. So from this equation, that is A, and from B, if we calculate the temperatures T1 and T2, so T1 from A will be ln R2 by R1 into QR by Ka 2 pi L, and T2 T3 is ln R3 R2 QR Kb 2 pi L, and if we're going to add both these equations, we're going to have the temperature difference between T1 and T3, which is QR taken out ln R2 by R1 by Ka, and we can take 2 pi L as constant plus ln R3 by R2 over Kp. So QR is 2 pi L into T1 minus T3 over 1 by Ka ln R2 by R1 plus 1 by Kb ln R3 by R2. So in this way, for the composite cylindrical systems, we can calculate the heat transfer rate. Now in a spherical system, obviously it again we can solve in a similar way, but in the spherical system, the area will be 4 pi r square, and then we can integrate from R1 to R2, from the temperature T1 to T2. We can have the same derivation for the spherical systems. For the spherical systems, you can derive this heat transfer rate. It will be represented by 4k T1 minus T2 over 1 by R1 1 minus R2, because over there in the integration factor, that is over here, the area will be 4 pi r square. So when you're going to integrate, you're going to get this term as 1 by R1. So from R1 to R2, you can calculate the heat transfer rate. So that's it for the simple heat conduction through three different systems, from the rectangular system, from the cylindrical system, and from the spherical system. And also we've considered the composite systems. So tomorrow, maybe in the next lecture, we're going to start with the heat source problems, where the heat source is present at one particular location and how the heat is being transferred from one particular position towards the another through a cylindrical systems as well as through a rectangular system. And then we'll move towards the heat convection. Thank you.